You ever get that feeling the universe is just, well, doing things? Like, it's not static, right? It's constantly changing, moving around, maybe even hiding something from us. What if we could finally get, like, the ultimate surveillance footage? A cosmic film. One that reveals all the hidden forces really at play, showing us what's really pulling the string. Because, maybe we aren't just observers in this whole grand cosmic drama. Perhaps we're about to uncover something, well, truly unexpected. Welcome to Cool, Weird, and Possible.
Today, we are diving into exactly that idea. The universe in motion, Rubin's cosmic film. And this isn't just about, capturing pretty pictures of distant stars, though it does that too. It's really about observing the entire universe in an unprecedented time lapse, seeing it move, seeing it evolve, almost in real time. We're focusing on the Vera C. Rubin Observatory's legacy survey of space and time. They call it LSST, and it's, well, frankly, revolutionary 3.2 gigapixel camera. Over the next 10 years, this incredibly ambitious project is set to create this dynamic chronicle of the cosmos. And it's likely going to completely reshape our understanding of pretty much everything out there, from the smallest asteroids zipping around nearby to the most profound mysteries like dark matter and dark energy. Okay, so let's unpack this cosmic movie machine a bit. When we call it revolutionary, we genuinely mean it. The Rubin Observatory, it's perched high up in the Andes Mountains in Chile. And it isn't just another big telescope. Its centerpiece is this sprawling 3.2 gigapixel camera. Just for context, that's nearly 200 times larger than even the most high-end camera you could buy today. Yeah. Imagine trying to capture the entire night sky, like every star, every galaxy, in just breathtaking detail, and doing that multiple times a week, every week, for a whole decade. So yeah, this isn't just a bigger lens. It's like a completely new way of seeing the universe.
Absolutely. And what's truly fascinating here is the sheer ingenuity behind the camera's digital film, so to speak. Brookhaven Lab played a really pivotal role in developing this core component. This isn't your old celluloid film, obviously. It's an incredibly sophisticated sensor array. It's made up of 201 individual charge-coupled devices, or CCDs. You can think of each CCD as a super-sensitive digital eye, basically, designed to capture photons coming from across the universe. These are then grouped into 21 larger units they call rafts, and each raft holds 9 of these sensors. What makes these CCDs so unique is their incredible sensitivity. They can capture light far beyond what our human eyes can perceive, from ultraviolet all the way to near infrared. Plus, and this is crucial, they boast an exceptionally fast readout time, which you absolutely need if you're going to build that rapid time lapse of the entire sky. This kind of unparalleled sensitivity and speed, they aren't just technical feats, right? They're really the only way to capture those fleeting, subtle changes across the vastness of space. It turns what we once thought of as a pretty static sky into, well, a living, evolving cosmic movie.
That just sounds like an astronomical amount of data, though. I mean, how on earth do they even begin to handle a cosmic film with that much detail? Are we talking about some kind of, I don't know, secret underground data bunker hidden somewhere? Or maybe a server farm powered by cosmic rays? Because the scale just feels almost unmanageable.
Yeah, well, the image of a secret bunker is certainly dramatic, isn't it?
Yeah.
But the reality is actually equally impressive, just in its scale and how distributed it all is. The design philosophy of LSST is famously wide, fast, and deep. And that translates directly into this enormous data volume. Each single image captured is approximately 8 gigabytes, and the observatory captures more than 1 image per minute. So to put that into perspective, every single night, Rubin generates around 1,000 scientific images, plus about 450 calibration exposures. That adds up to roughly 20 terabytes of data that needs to be shipped physically and digitally daily, from Chile all the way to SLAC in the U.S. for the initial processing. And over its planned 10-year survey, it's going to accumulate an astonishing 50 petabytes of raw data. That's 50,000 terabytes.
50 petabytes, wow.
Yeah. And 50 petabytes isn't just a number, right? It represents this comprehensive, dynamic record of the universe's evolution. This isn't just seeing snapshots anymore. It really is like watching an entire film of cosmic history unfolding, revealing processes that happen over millennia, but we're seeing them through these real-time observations. Now, to manage this cosmic deluge, the data processing and storage, they aren't confined to just one location. It's meticulously distributed globally. There are major facilities in the US, in France, and in the UK, all working together. This ensures redundancy, sure, but also accessibility for researchers all over the world.
Okay, so this camera can see the universe in motion, capturing just incredible detail. But what about the things we can't see? The sources we looked at mentioned that a whopping 96% of the universe is still a complete mystery. I mean, 96%. Are we talking about cosmic shadows? Or maybe hidden forces we're just not supposed to know about lurking just beyond our perception? Because that number is just absolutely mind-boggling.
It really is. And that truly raises one of the most profound questions in modern astronomy. It's certainly one of the primary drivers for building LSST in the first place. You're absolutely right that 96% of the universe is indeed shrouded in mystery. It's accounted for by two tremendous unknowns: dark matter and dark energy. Dark matter makes up about 25% of the universe's total mass and energy. It doesn't emit light, it doesn't absorb light, it doesn't reflect light, so we just can't see it directly. And yet, it acts as a kind of invisible galactic glue. Its gravitational pull holds entire galaxies together and even forms the cosmic scaffolding upon which the visible universe is built. Then there's dark energy, which is even bigger. It constitutes a massive 70% of the cosmos.
70%.
70%. This is the mysterious force that's driving the accelerating expansion of the universe. It's what started pushing everything apart faster and faster sometime after the Big Bang, and it continues to do so today. So LSST aims to illuminate these profound mysteries in some really remarkable ways. For dark matter, it uses a technique called gravitational lensing. Imagine looking through a distorted pane of glass. The background appears warped, right? Now, imagine space itself is that pane of glass. Dark matter, even though it's invisible, is so massive it actually warps the very fabric of space and time around it. LSST will meticulously map how the light from billions of distant galaxies gets stretched and bent by this invisible mass. It's essentially creating a detailed cosmic distortion map that reveals exactly where the dark matter is hiding and how it's distributed across the universe. And as for dark energy, well, since LSST is designed to track cosmic movements over time, its images will provide some of the most precise measurements ever of our universe's accelerating inflation. Think of, like, a siren's pitch dropping as an ambulance drives away. That's the Doppler effect for sound.
Okay, yeah.
Light does something similar. As distant galaxies are carried away from us by the universe's expansion, their light waves get stretched to longer, redder wavelengths. We call that redshift. Rubin will measure this stretching with unprecedented precision across billions of galaxies. By seeing how much the light is stretched and how that stretching changes over cosmic time, we can pinpoint the rate of the universe's accelerating expansion. That gives us profound insights into dark energy's nature and maybe even the ultimate fate of the cosmos itself. It's like seeing the cosmic anti-gravity in action.
Huh. So this telescope is basically a cosmic detective then. It's trying to figure out what's really driving the universe, or I guess pushing it apart, as it were. It's trying to unmask these invisible forces shaping everything we see. Okay, here's where it gets really interesting, at least for me. The sources tell us that after its 10-year run, LSST will essentially create this stunning, dynamic, time-lapse movie of the entire universe. Like you said, this isn't just a static collection of pretty pictures. It's a living, breathing, dynamic record of cosmic evolution.
That's precisely right. And this movie, it isn't a single continuous shot like we think of a regular film. Instead, it's constructed from thousands upon thousands of what you could almost call penny-sized frames, relatively speaking. The observatory will systematically scan the entire visible sky every few nights. Usually takes about 3 to 4 days to form one complete picture or frame of the whole sky at that specific moment. By repeating this process religiously, night after night, year after year for 10 years, we get that incredible time-lapse effect. It captures everything from changes that unfold over mere seconds, like an asteroid moving, to those that span cosmic ages. What's even more impressive, I think, is the capability for near real-time discoveries. LSST will process and upload something like 100,000 updates every single night.
100,000?
Yes, almost immediately announcing transient events. We're talking about everything from the subtle drift of a newly discovered asteroid to the dramatic flicker of a dying star going supernova. These alerts go directly to researchers and interested astronomers worldwide. This rapid alert system means scientists can actually follow up on these events with other telescopes almost as they happen. It's incredibly powerful.
And these first look images, I mean, even from the commissioning phase when they're just testing things out, are already showing some truly wild stuff. We're hearing about quadruple interacting galaxies colliding, these mind-numbingly huge voids of just nothing out there. It almost makes you wonder, could these images be glimpses into, I don't know, other dimensions? Or maybe even like what one comment suggested online, a vein of an alien, some cosmic structure so organic and strange it just defies conventional understanding.
Well, we can certainly confirm the observation of incredibly complex interacting galaxies. A great example is the famous Stephan's Quintet, which is this highly active group where galaxies are literally colliding and merging. It's spectacular. And yes, the universe does indeed have this vast cosmic web structure. You have these long, expansive filaments where galaxies cluster, and they're interspersed with these truly mind-numbingly huge voids of, well, almost nothing. It definitely paints a picture of a universe that's far from uniform. It's lumpy, it's structured. But on a more immediate and tangible note, one of LSST's critical missions is actually planetary defense, protecting Earth. It's expected to detect about 130 near-Earth objects, or NEOs, per night, just in its first year of full operation.
130 a night.
Per night. This means it could potentially find around 97% of all potentially hazardous asteroids out there, the ones that pose a potential threat to Earth. That's an absolutely significant win for planetary defense. In fact, it has already discovered approximately 2,100 new asteroids from just 10 hours of commissioning observations. Just testing. It's a testament to its raw power.
Wow. And speaking of exciting prospects, maybe closer to home, this idea of Planet 9 keeps popping up. The sources mention Mike Brown, the astronomer associated with Pluto's controversial reclassification, suggesting Rubin is the telescope that could finally find it. He even went as far as predicting its existence could be known by, December 2025, if commissioning starts as planned. So beyond the distant galaxies and the cosmic voids, what does all this mean for our immediate cosmic neighborhood and, I guess, ultimately, our very place in the cosmos?
Yeah, the Planet 9 is definitely one of the exciting possibilities. And if we connect this back to the bigger picture, this cosmic film isn't just for, casual viewing or tracking known objects like asteroids or potential planets. It's fundamentally designed to unlock answers to some of the deepest questions about the universe's origins and its fundamental building blocks. LST plays a crucial role in probing various dark matter models, trying to figure out what this invisible stuff actually is. We're talking about different theories. There's warm dark matter, or WDM, which suggests dark matter particles are relatively light and fast-moving, maybe like neutrinos. Then there's self-interacting dark matter, SIDM, which proposes these particles can actually bump into each other, potentially explaining some weird things we see in galaxy structures. And critically, there's this renewed interest in compact objects like primordial black holes or PBHs.
Primordial black hole.
Yeah, these are hypothetical tiny black holes, not formed from collapsed stars like typical black holes, but theorized to have formed in the extremely dense conditions of the very, very early universe, fractions of a second after the Big Bang. The key method here for probing these kinds of models is again that microlensing technique, where we observe how the light from a background star is temporarily magnified and distorted as a compact, massive foreground object, like maybe a PBH, passes directly in front of it from our point of view. What's truly fascinating and has really spurred interest recently is that the LIGO observations of merging black holes, well, some of them were surprisingly heavy, between 10 and 50 times the mass of our sun.
Heavier than expected.
Heavier than typically expected, just from stellar collapse alone. This has significantly renewed interest in PBH dark matter as a potential explanation. LSST could potentially detect these high-mass black holes, the ones over 30 solar masses, or maybe even black hole clusters, through these microlensing events. Now, if we find robust evidence for those, multiple events pointing to a population of these objects, that would be a veritable smoking gun for PBH detection. And such a discovery, it wouldn't just confirm a completely new type of black hole, it could force a complete reinterpretation of other particle physics limits. It would fundamentally change our understanding of the universe's initial conditions and how dark matter behaves. It's huge.
So essentially, this telescope could confirm if these weird cosmic anomalies are actually tiny black holes left over from the Big Bang, or even, as some, Reddit users suggested way back when looking at early deep space images, maybe if alien civilizations are out there just deciding we're unworthy of their attention and hiding behind some kind of celestial curtain.
Well, while the idea of alien civilizations is certainly a captivating thought for many, the immediate scientific goal for Rubin is definitely focused on understanding the universe's fundamental components and dynamics. Shedding light on what we do know is there, but just can't see directly, like dark matter and dark energy. And to that end, it's worth noting Rubin's images are captured in what they call real color. They combine ultraviolet, visible, and near-infrared light. This isn't just for making pretty pictures. It allows us to analyze the universe across a much broader spectrum, closely matching what our own eyes would perceive if they were, vastly more powerful. And this incredible volume of data, it isn't locked away in some vault. It's made widely available through a pretty sophisticated system called the Rubin Science Platform. This platform offers different data products, tailored for various research needs. There's prompt data for those rapid discoveries and transient event alerts we talked about. Then there's the main data release for comprehensive, carefully calibrated studies of the entire sky over time. And importantly, there are also user-generated data products. This allows the whole scientific community to collaborate, run their own analyses,
and contribute back to the research effort. This commitment to open data is really key. It ensures widespread access to this cosmic information, truly empowering a global collaboration among astronomers.
You know, looking at these images and especially reading the reactions from people online, there's just this overwhelming sense of scale, isn't there? So many people describe feeling small and insignificant, or even like bacteria on some tiny cosmic speck floating in the void. What stands out to you about how these images and just the sheer scale of the universe they reveal impact our human perspective? Does it have to be diminishing?
That's a great question. And what's truly fascinating here, and perhaps offers a counterpoint to that feeling of insignificance, is the monumental human effort behind this entire project. It really is a testament to what global collaboration can achieve when we put our minds to it. The UK, for instance, is the second largest international contributor to the Rubin project. They're playing a crucial role in managing and processing something like 1.5 million images. This enormous data stream will eventually help catalog around 10 billion stars and galaxies.
10 billion.
10 billion. This level of international collaboration isn't just about sharing resources, like money and equipment. It's about sharing expertise, bringing diverse perspectives together, and building this collective understanding of the cosmos that no single nation could possibly achieve alone. For me, that's a profoundly hopeful aspect of this whole endeavor. It shows what we can do.
It is incredible to think about this massive global scientific undertaking, all aimed at creating this cosmic film. But, I have seen some chatter online about how something as grand as this could actually be impacted by, well, more earthly matters, mundane stuff. Are there any real threats to this ongoing survey? Could this monumental effort simply, I don't know, lose power or just get unplugged because of budgets?
Unfortunately, yes. This raises an extremely important and, frankly, pressing question about the real-world challenges facing this kind of groundbreaking astronomical research. The National Science Foundation, the NSF, which is a primary funder for Rubin and really a cornerstone of U.S. scientific research across the board, is currently facing potentially substantial budget cuts. Specifically, there's a proposal that could mean a 57% reduction in their 2025 budget for astronomy facilities.
57%, that's huge.
It's a massive cut, and the implications are severe and really far-reaching. It directly impacts the grants that support the next generation of scientists, the students and postdocs, who are absolutely crucial for analyzing this immense data set from Rubin and driving the new discoveries. Beyond that, it affects essential follow-up telescopes, like the Very Large Array, the VLA, down in New Mexico. VLA is vital for complementing Rubin's broad sky surveys with detailed radio observations of interesting objects. Well, the VLA is facing a staggering 30% cut under current proposals. This leads to what's grimly termed reduced operations, which basically means potential staff reductions and the telescope just sitting idle for significant periods, even when astronomers need to use it.
So the telescope just sits there?
Potentially, yes. Idle time. This isn't just about money, it's about the very pace of discovery. It's about the potential for groundbreaking science to be delayed, or maybe even lost entirely. And it affects the continuity of our exploration of the universe. It's a really stark reminder that even the most ambitious cosmic endeavors are ultimately grounded in these very earthly realities of funding and political decisions.
Wow. It's wild to think that something as monumental as creating a time lapse of the entire universe, trying to solve mysteries like dark energy, could be affected by something as, well, down to earth as funding debates. It really does put things into perspective, doesn't it? The grandest scientific projects are still very much tied to human decisions right here.
And, as we gather more and more of these incredible images, and with every single new discovery, the universe only seems to get bigger and honestly weirder. It truly makes us question not just what's out there in the darkness, but what we're really looking for when we stare up. And perhaps, just perhaps, what might be looking back. Thank you for joining us on this deep dive into the universe in motion, Rubin's cosmic film, here on Cool, Weird, Impossible. Make sure you subscribe to our channel so you don't miss our next deep dive into the unknown.